Hello everybody. So we are gonna solve now an example for the Langmuir-Hinchelwood kinetics in Aspen Plus. And this is an example that we mentioned in the previous video about the methanation reaction where carbon dioxide reacts with hydrogen to form methanol. And we have a side reaction which is the water gas shift reaction. We know all the conditions of the feed, the temperature, the pressure, and the flow rates of the components of the feed. And we know that it's a PFR with 8,000 tubes, and each is 12.2 meters long, and the diameter is 3.75 centimeters. So we kind of know everything, and we know that the reactor is assumed to be isothermal at 220 degrees Celsius, and we know some information about the catalyst, about the particle density, and the porosity. And we mentioned in the previous video that we know the kinetics of the reaction, and we know that it follows the Langmuir-Hinchelwood kinetics, and this is the kinetics of the main reaction, which is the carbon dioxide plus hydrogen giving methanol and water. And this is the side reaction, which is the water gas shift reaction. It's carbon dioxide plus hydrogen giving carbon monoxide and steam and water. Vapor. So, and this is the kinetics of the reaction. So before going to Aspen Plus, I would like to kind of go into details of the definition of the reaction kinetics in Aspen Plus. Because it's not a straightforward thing that can be understood easily. So I'd like to spend some time demonstrating how we are going to put the numbers in Aspen Plus so that you understand what we're going to do later. So this is the main reaction, and we mentioned that the numerator is the driving force multiplied by the kinetic factor, this is the kinetic factor, and this is the partial pressures of the reactants, and this is the same thing for the second term. So we have two terms in the numerator. Each one of them again consists of the k. This is all considered k forward, and this is all considered at the k backward. And then the partial pressures with the exponents that we have here. So as we mentioned in the previous video, the kinetic factor is defined using this equation. This is how Aspen Plus understands the kinetic equation, the kinetic factor. So it's in the form of exponential of a multiplied by exponential of b over t multiplied by t per c multiplied by exponential dt. And we have to put the values of a, b, c, and d that will make this equation is equal to this form. So this is our task now. So I see here that there is a constant here which corresponds to exponential of a, and there is exponential of a number over t which is corresponding to this term, and we don't have anything else, so c and d will be equal to 0. So I'm not gonna have anything to put here but zeros for c and d, so these terms will be cancelled out. So from this I know that exponential of a equals this number, which is this number, and this means that a equals ln of this number, which is negative 29.86. And b is straightforward. I don't have to do any calculations to get b, so it's going to be 4413.76. So these are the values of a and b that I need to put or define to Aspen Plus in the k forward term, so that I define it this way, so he understands, the software understands that this is what I am entering. And I have here the exponents for the carbon dioxide and hydrogen. Both are 1. This is per 1 and this is per 1. The negative term is not included in the second term. So the second term is the what we have after the negative sign. So it takes the same form. So this is corresponds to exponential of a. So a is gonna be 17.549. And the b is negative 2645.966, which is this term, and I have the exponents methanol and water are 1, and hydrogen is -2. So this is not it's not difficult to define. As long as you understand this equation, it's going to be a piece of cake. However, for the adsorption term, it is not that easy. For the adsorption term, it has to be defined separately. Each part has to be defined separately. So we have this bracket raised to the power of 3, and this bracket contains 4 terms. It can be more, but in our case it's 4, and other cases might be less, but in our case we have only 4. So I have to define each one of these like dotted lines separately, because this is the way the software understands our inputs. So this is the hint that comes in Aspen Plus, that it takes the form a plus bt, and this is the coefficient, each one of these coefficients. So I have each one of them consisting of a number multiplied by partial pressures, combination of partial pressures. I have here as number, whatever number multiplied by exponent of something, and then a combination of partial pressures, and so on. And this is the tricky part, that what I did in the previous slide for the kinetic factor is gonna be similar to what I'm gonna do here, but this is done for 1, 2, 3, 4 terms. So it's done for 4 terms. And it's kind of not that easy, because it's in the form of ln of the constant I, which is this or this or this or this, is a plus bt, b over t plus c multiplied by ln t plus d multiplied by t. So we can take the exponent of both sides, so it's gonna be the same shape that we mentioned in the previous slide. So if we go back here, it is the same shape. And this is the way, again, it is defined. So I'm gonna do the same thing, but for 4 terms. The way that we define it to Aspen Plus is kind of hard to understand, or hard to grasp easily. And it took me personally some time until I understood how this is defined in Aspen Plus. So I put this table with colors so that each color matches each one of these terms. We have here, this is the exponent of 3, so it's going to be just put easily, just a number that we put. And now we will go to this term and compare this to this. So I want the coefficients a, b, c, and d that will make this term equals to 1. And this is easy. I'm going to put a, b, c, and d all equal to 0, which I have here for term number 1, which is the brown one. A, B, C, and D are equal to 0, and I have no partial pressures here, so the exponents are zeros. So this is easy. Now we go to the second one. We have a constant multiplied by partial pressures. So the constant term is the exponent, so I'm going to take the ln of this number. So this is the term A for the second term, the parameter A. B, C, and D are zeros because we don't have any exponents here or any other terms here. For the third term, it's going to be the same. It's a constant, so I'm going to take the ln of this constant so that I can get the value of A for the third term, the green one. But here we have an exponent of something over t, which corresponds to this. So B is going to be this number, which is this number. For term number 2, we have, I forgot the exponent, so I have water of exponent of 1, the partial pressure of hydrogen of exponent of -1. Here we have partial pressure of hydrogen for term number 3 of exponent of 0.5. And for the third term, our fourth term is going to be the same. Exponent of the ln of this is going to give us the term A, or the A for term number 4. And this 14928 is the coefficient B for the term number 4, and no C and D, and the exponent of hydrogen of water is 1 with no other partial pressures. So this is how we're going to define it in Aspen Plus. I know it's a tedious process, but this is how we define it. The same thing is going to happen for the side reaction. I'm going to define A and B for the parameters or the coefficients A and B for the forward and the backward reaction. And the absorption term for the side reaction is the same, with just the exception of the exponent is 1. I'm sorry, this is the side reaction. I didn't change it. So this is the side reaction. So this is all what we need to do. So what I'm gonna do now is I'm gonna open Aspen Plus. So I hope this explanation made life easier and kind of easy to understand for what's coming next. So what I'm gonna do now is I'm gonna put the 2 windows for the slides that I have here and the Aspen Plus window side by side. just before we start with the simulation software, I'm gonna mention that I have chosen the method is the SRK because we are operating at very high pressures. We are operating at I think it was 110 bars, so it's high pressure, then more than 10 bars. So in this case we use cubic equation of states, so you can use SRK, Penn-Robinson, or any one of these. In the simulation, I have already, just for the sake of time, I have already defined the feed stream, all the temperature, the pressure, the composition or the flow rates of the components, and I defined the product stream. I just connected it, I didn't define anything. And for the reactor, I have defined all the information that I have. So it's a specified temperature of 220, and it is multitubular with 8,000 tubes, 12.2 meters long each, and the diameter of each 3.75. It's vapor phase. And for the catalyst, I put the information that I know for the voidage and the particle density. So I have everything that we mentioned in the previous video of the PFR. And now we will go to the new tricky part, which is the definition of the reaction. So I'm gonna define a new reaction. I'm gonna call it R1, and it is Langmuir-Hinchelwood kinetics. And we will go to the reaction tab to see what we're gonna do. So I have to define the reaction. So it's a new reaction. I have actually two reactions. So just to prevent any confusion, I'm gonna use this equation to be easy and easy to follow. So I have CO2. And the coefficient is -1. I have hydrogen, and it's -3. And for the products, I have methanol of coefficient of 1 and the water coefficient of 1. So these are the stoichiometrics of the first reaction. I need to define a new reaction, which is the side reaction, the water gas shift reaction. So I have CO2 coefficient of -1, hydrogen coefficient of -1 as well, and the product is CO coefficient of 1 and water coefficient of 1. So I now did the definition of the stoichiometric coefficients of the two reactions, and now let's go to the fun part. We have here the two reactions. It's similar to the power law kinetics, but we have here some buttons that were not before or shown before, the driving force and the absorption terms. So this is a vapor phase reaction because we are working at high pressure with volatile components, and the basis is going to be the either we can choose the reactor volume or the catalyst weight. So I'm going to make it the catalyst weight because it's a catalytic reaction. For the kinetic factor, it's going to be the term that is before the bracket and multiplied by the whole bracket, and I don't have any term here, so I'm going to make it 1 for the K, and the E is equal to 0. So by doing this, I have this whole term equals to 1. So I'm just putting the kinetic factor equal to 1 because I don't have a kinetic factor. It's simply 1. And now I'm gonna go for the driving force, and I'm gonna follow what I mentioned here. So the basis is the partial pressure, and now we have two terms. This is term number 1 and term number 2, and here just keep in mind that there is no option to add any terms because it has to be only two terms in the numerator. So this is term number 1. I have the exponents of carbon dioxide. This is the term number 1. The carbon dioxide is, or carbon dioxide is 1, hydrogen is 1, methanol is 0, and water is 0. And the coefficients here for the term number 1 is A equals -29.866, B equals to 4413.76, and this is all for term number 1. C and D are equal to 0. Now we will go to term number 2. It has the coefficients of carbon dioxide 0, for hydrogen -2, for methanol 1, for water is 1, and the coefficients are 17.549 and -2645.966. So these are all the information that I have to define for the main reaction about the driving force, or the numerator of the kinetics. Now let's go to the second part, which is the adsorption. I'm still working with the main reaction, so I'm gonna go for the adsorption term and just try to match what we have here with what we have here. So I have here for the concentration exponents, which are these partial pressures that are raised to powers of whatever. I have only water and hydrogen. I don't. This is hydrogen. This is water. So I have only water and it misunderstands the enter button here, so I'll try not to click on the or press on the enter button. And this is hydrogen. For term number 1, I have 4 terms here, the brown, blue, green, and yellow. So term number 1, I have 0 for each one of them. And for term number 2, I have the exponents for water is 1 and hydrogen is -1. And for, I didn't put the exponent of 3. This is the adsorption expression exponent, which is this 3. And for term number 3, we have 0 water and hydrogen is 0.5 and 0.5. And for term number 4, we have water 1 and hydrogen 0. So I'm done with these concentration or partial pressure exponents. Now we have again 4 terms here, so I'm gonna put 1, 2, 3, and 4. And keep in mind here that you have the freedom to add as many terms as you want, because this is possible in this kind of kinetics. It's not possible again in the numerator. You have only available, or you can add only 2 terms, or define 2 terms. Okay, for term number 1, which is this, I have the coefficient A is 0. For term number 2, coefficient, this is term number 2, coefficient A is 8.147 and coefficient B is 0. For term number 3, we have coefficient A is 6.452 and coefficient B is 2068.44. For term number 4, it is 34. The A is 34.951 and for coefficient B is 14,928.915. So I'm now done with defining the denominator or the adsorption term for the main reaction. If I click next, it's gonna close the window, and I need to go to the last part, which is the kinetic or the adsorption term, or defining the side reaction totally. So again, I don't have kinetic factor for the side reaction. E is 0, and I'm gonna make it as a vapor phase and the catalyst weight. For the driving force, I'm gonna do this is partial pressure. Term number 1, I have carbon dioxide. All the rest of the terms are zeros. For A is 4.804. For B is -11,398.24. I'm done with this term. For term number 2, it is 0.132. I'm sorry. This is the exponents is carbon dioxide is 0, hydrogen is -1, for carbon monoxide 1, water is 1, and the coefficient A is, we are here, it's 0.132, -6624.98. And now I'm done with the driving force term, and I'm gonna go for the adsorption term for the side reaction. The exponent here is 1. This was the main difference between this reaction and the main reaction. And I'm gonna put everything. I have the components that I have are water and, oh my god, it is water and hydrogen. I have 4 terms, 2, 3, and 4. And for the concentration exponents for term number 1, I have water. This error is kind of common error. It's not a problem, just mentioning that the maximum number of terms cannot be or the adsorption constant cannot be greater than the maximum number of terms. It means that the number of terms here has to be equal to the number of terms here. So we have 4 here, so we need to add 4 here. So it's not a big deal. You can still work with it. So for the exponents, I have for term number 1 0 and 0. And it's gonna add a new column. For term number 2, the exponents are this is term number 1. Term number 2, we have water and hydrogen, -1. For term number 3, we have 0 water. I'm sorry about that. It's kinda click that I'm used to. For term number 3, we have water 0 and hydrogen is 0.5. Finally, for term number 4, we have water of 1 and hydrogen is 0. And now we come to the last part here, which is putting the coefficients. For term number 1, all are zeros. For term number 2, we have A equals 8.147. For term and B equals 0. For term number 3 is 6.452. And for term number 4, A equals 34.951. And for term number 3, B equals 2068.44. For term number 4, the coefficient B equals 14,928.915. So we're now done with everything. And as you saw, it took me a long time just to put the numbers, because we are putting numbers here, we're putting number for driving force, we're putting numbers in adsorption, and there are a lot of numbers. So I really recommend that you make tables like these in case you are working with the Langmuir-Hinshelwood kinetics, because there is a very, very big chance of doing mistakes. If you are not well organized and you know which number is going to go where, you will most probably have problems with entering the numbers. And finally, we are going to go back to the reactor, go to the reactions, and we have already added this reaction to the reactor, and we can now run the simulation. And by clicking on run, we will wait for a few moments until all the calculations are done, and we will see what we are gonna get. Just now calculating, so now the results are available. We don't have errors, so that's nice. And now we'll see the results. There is heat duty. And it's kind of expected, because we said that this reactor is isothermal, so it means that we don't have any or we're keeping the temperature constant, so we have to have a heat source or cooling or heating outside so we can maintain the temperature. I would like to see how much conversion we achieved using this reactor after all this. Oh, we don't have any conversion. This is weird. So let's go back to the inputs and see what we have. Maybe we did something wrong. So we have the hydrogen, carbon monoxide, carbon dioxide. These are the feed. So I just paused for a while just to figure out what's the problem, because the troubleshoot process sometimes takes some time. And I figured out the problem, and I'm glad that this problem happened, because it's a good demonstration of how one wrong number might make problems. So this is what we mentioned, perhaps of the absorption term, perhaps because I was not showing it as big numbers. Let's keep them side by side. I'm sorry about that. I'm gonna keep them side by side and to see what is the problem. And again, it's important to revise the numbers, because you're probably facing some problems like the ones I'm facing now. There is a negative sign here and there is a negative sign here. I didn't see them because the numbers were small, but now I have them here for both reactions. So this is the main reaction, this is the side reaction, and this is kind of nice to see that how the just one sign can ruin everything. And this is because it's messing up with the adsorption term, which is again one part of the steps of the reaction. So I'm done. I'm gonna run the simulation and now look at the stream results, and I hope it is working now. Okay, so now it works. So now we see that there is some change. We had here, it's not a big change, but there is a reaction taking place here. So we have hydrogen is consumed, and we have some of the hydrogen is consumed, and some of the carbon monoxide is consumed. Again, let's go back for the main reaction, because I totally forgot what the reactions that we were working for after all this hassle. So the main reaction was carbon dioxide and hydrogen. And here, I'm sorry, and here for the hydrogen we had some consumption, for the carbon dioxide we had some consumption. It seems that the reaction rate is not very high, or the volume of the reactor that we are using is not good enough. I think one thing that I did was not right in the reactions, in the kinetics part here. I changed it to reactor volume, and it should be the catalyst weight. It was just one of the trials that I was doing to fix everything, and this will definitely have an effect on the results. So going back to the stream results and going back to the mole flows, yeah, this is the numbers that we should expect. So we had some reaction taking place. Again, it's not a lot of reaction, but there is a reaction going on here, and we have methanol produced out of the reactor. We can go here and see the profiles that we have here for the temperature, for the temperature is constant. For the we can take a look at the concentrations, the molar compositions. We see that methanol is increasing, water is kind of increasing, and carbon monoxide is kind of changing, but not very much, and hydrogen is consumed somehow. And now if we take a look at the temperature, I mean the profile for, I would say, for methanol and for hydrogen, one of the reactants and one of the products, it seems that there is some consumption here, and there is some I mean production and consumption, and it seems that the rate of reaction is not very high. So maybe it's better to change the conditions of the reaction. For instance, for the PFR, I can change the reactor temperature to make it, for instance, 150, and see for the feed temperature, and see how the composition changes, and the rate is very slow here. So it's nice to see how the parameters are affecting the reaction. So I have to increase the reaction, so I could make it like 250, and see what results that we're gonna get. This is the composition. It's getting better, so I have more production of methanol. So you can play with the parameters. For instance, if I change the pressure, it's 110 bar. If I make it 50 bars, I'm just trying. Using this kinetics, I can see how this changes, and it seems that it's not changing a lot. But anyways, the reaction is going on now, and we see that we have already defined all the terms. I'm like eager to stress on the point that it's important to understand how Aspen Plus understands your input and how he expects your input to be, so that you're telling him what you want to tell him. So I hope it's like a good demonstration, and I'll see you in the next video, inshallah. Goodbye.